So let's work through some examples about functions. In this question, which of the equations represents y as a function of x? So in order to determine if either of these are functions, the first thing we need to do is we need to solve the equations for y. So here, let's subtract x squared, and we get y equals negative x squared plus 1. In this case, for each value of x, there would be a particular y value. So yes, this does in fact represent a function. For b, again, we're going to solve for y. So add x to both sides, you get y squared equals x plus 1. Then I have to square root both sides. Recall that when you square root a variable that you get two possible results. So this is a plus or minus, square root of x plus 1. So this tells us that if we put in, for any x value that we put in, we would actually get two results for y. So therefore, this is not a function because a function is defined as having one unique y value for each x value. In this example, we're going to talk about domains. So we've got 4 examples to talk about the domain of the function. In letter A, the function is given as a list of coordinate pairs. And we recall that a domain is the set of all inputs. And in a coordinate pair, the inputs are the x values. So for A, we would just list the coordinates. We would list the x coordinates from each point. So -3, -1, 0, 2, and 4, that would be our domain because those are the input values to get those y values out. For B, we're looking at this equation, and recall that a domain has to provide outputs. So for every input, you have to have an output. And in this case, the function is a fraction. And recall that fractions have to have sort of a limited domain because there are certain things that are undefined in fractions. For example, when when the value of the denominator is 0, the fraction is undefined. So for part B, even though we have this whole function, we're most interested in what's happening in the denominator. What would make the denominator equal 0? So we can set it equal to 0 and solve. And that is the part that we have to eliminate from our domain. So our domain would be the set of all real numbers such that x does not equal -5. So it can be anything except for -5. All right, let's look at C. For example, C, they say the volume of a sphere equals 4/3 pi r cubed, where r stands for the radius of the sphere. So if we think about C, we have an actual equation which represents actual measurements of things. So this is the variable that we're concerned about. What measurements make sense if you're talking about an actual sphere? Can you have a sphere with a radius of 0? Yeah, no, because your sphere wouldn't exist if the radius was 0. Can you have a sphere with a negative radius? No, because who knows what that is? Some sort of wormhole, black hole dimension. Who knows? So we need all of our r values to be greater than 0. So our domain is going to consist of all of the r values that are greater than 0. even though we would get values out if we put in values that were, if we used inputs that were less than 0, they wouldn't make sense in the context of this example. So we exclude them from the domain. And finally, let's look at D. D says that we have this function, the square root of 4 minus x squared. What do we know about square roots? Well, they're only defined when they are greater than or equal to 0. So we take that expression and we set it equal to, or we make it greater than or equal to 0, and then we're going to solve. So square both sides, 4 minus x squared, greater than or equal to 0. We're going to subtract 4 to the other side, negative x squared, greater than or equal to negative 4. Square, divide each side by negative 1 to change the signs, and recall that when you divide each side by 1, you have to flip your inequality, negative 1. Multiplying or divided by negative, you flip your inequality. Now we can square root both sides, and we get this. So x is less than or equal to plus or minus 2. So what do we do with that information? Now, this problem is a little bit more complicated just because we've got a quadratic inequality. So what we'll get to this later, but what ends up happening is you kind of make a number line, you would put negative 2 on the number line and positive 2 on the number line, and then you would test values. So like you would test a value here to see what happens, you would test a value here to see what happens, and you would test a value here to see what happens. And in this case, what would happen is the green and the pink, those would give us complex numbers and imaginary numbers. So that means that our domain must be the yellow part. So we would go ahead and say, oops, that's a highlighter. We would go ahead and say that our domain in this case would be between 2 and negative 2. And we can write it as an inequality like that. Oh, and there, sorry, it's inclusive. So those two parts are included. Okay, example 6. You work in the marketing department of a soft drink company and are experimenting with a new can for iced tea that is slightly narrower and taller than a standard can. So imagine the LaCroix skinny cans. For your experimental can, the ratio of the height to the radius is 4, as shown in figure 1.4, which I redrew over here. So here is my cylinder, here is the radius, here is the height, and the relationship between those two is this ratio, where the height to the radius, the ratio of the height to the radius equals 4. So we've got two parts to our problem here. We're going to write the volume of the can as a function of the radius r. So first of all, we need to know how to find the volume of a cylinder. So if you don't know, you go look it up, and you realize that the volume of a cylinder is equal to pi r squared h, where r is the radius and h is the height. So if we want to write the volume of the can as a function of the radius r, then that means we want r to be our input. And so everything needs to be written in terms of r. So we're going to have pi r squared h, but we can't have h's also. So we're going to take this information over here, and we're going to rearrange it to solve for h so that we can substitute it in. So if we took this thing, if we took that fraction and we solved for h, that means you would multiply by r on both sides. So you would have h over r equals 4, multiply by r on both sides, and you have h equals 4r. So this we can now substitute into our equation. So our equation would be pi r squared times 4r, and then we just clean it up. 4r is going to equal, V of r, volume with respect to r, is going to be 4 pi r cubed. So that's the volume of the can as a function of the radius r. Part B, they want the volume of the can as a function of the height. So again, we're going to use our basic equation, but instead of all of the values being in terms of r, now I want all of the values to be in terms of h. So I need to take my original ratio and I need to solve it for r now. So what that means is that you would multiply by r on both sides. We already did that, and we got h equals 4r, and now I'm going to divide by 4 on both sides to isolate r. So r is equal to h over 4. So now we want the volume with respect to h is going to be pi, but now we're going to substitute this in for r. So pi h over 4 squared times h. And then again, we're just going to clean it up. V of h equals pi times h squared over 4 times h, which is pi h cubed divided by 4. Oops, sorry, 16. 16. I did not square. I forgot. You square everything. Or I messed it up. 16, there we go. Pi h cubed over 16. Cool. So a baseball is hit at a point 3 feet above the ground at a velocity of 100 feet per second and an angle of 45 degrees. The path of the baseball is given by the function f of x equals negative 0.0032 x squared plus x plus 3, where y and x are measured in feet. And then they gave us this nice picture where it looks like that, which is a parabola, and this is distance horizontally, and this is height vertically. And for our equation, since this is the x-axis, that means that this is our horizontal distance. So the question is, will the baseball clear a 10-foot fence located 300 feet from the plate? So 300 feet from the plate is horizontal distance, and the 10-foot fence is vertical distance. So basically, we're trying to figure out if we put 300 into this equation as an input, will our answer be greater than 10 feet? Cool. Okay, so let's just do it. We're going to substitute in 300 everywhere there's an x. And we get out our calculators. Bloop, 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 bloop. And you get 15 feet. So this is going to be our vertical height. Is 15 feet greater than 10 feet? Yes, it is. So our answer would be yes. The baseball clears the fence. Home run. Or maybe it's a foul ball. We don't know. Okay, one last example, which is pretty important because it will be used all the time in calculus. One of the things that calculus aims to do is it talks about rates of change and changing rates of change and comparing rates of change. And so this difference quotient is a pretty key concept when you're talking about comparing rates of change. So think about a parabola for a moment. And a parabola is a nice curvy shape like this, compared to a line, which is a straight shape. And a line has a slope because it has a constant rate of change. A parabola doesn't have a constant rate of change. Its rate of change varies because depending on what 2 points you choose, the slope is going to be different. So for example, if I choose a point here and a point here, and I want to find the slope of that line, that's very different than if I choose a point, we'll choose this same point here and a point up here, right? Like you can see it as I draw them. Those two lines have different slopes. So what the difference quotient does is it says, all right, well, let's take these 2 points and let's make them super, super close together on the line. They're just like barely a smidgen apart. Because these lines that I drew, these are both secants because they touch the curve in 2 places. And what we want to do is we want to find the slope of the tangent, because the tangent touches a line in only 1 place. So if we think about these points, say I have this dot right here, and I want to find the slope of the curve at that dot. If I take this green dot, if I take this green dot and the blue dot and I draw a line between them, that's going to have a particular slope. If I take the red dot and the blue dot and draw a line between them, that's going to have a particular slope. And as this dot gets closer and closer, so like here's another little blue dot, the slope is going to keep changing, all right? And if I could bring those points super close together, then it's like they are a tangent, which is the slope at a particular point. So anyways, what this difference quotient does is it says, all right, well, let's call this point here, this is x, and just a little bit away from x here, some extra distance called h. So the distance from here horizontally to here is a distance of x, whereas this next horizontal distance to the red line, that's a distance of x plus h. So there's just a smidge more. So notice all we're actually doing is we're finding the slope. We're using the slope formula because this is y1 and this value is going to be y2. The reason the denominator is just an h is because actually we are using x is here and x plus h is here, and we're subtracting them. And when you subtract them, h is the only part that's left. Okay, that being said, you don't have to know everything about that whole formula because we're just checking it out for the first time. So if we're going to try and evaluate a difference quotient, what we need to do is we need to have an x value and a y value. Okay, so here's where this gets a little bit messy. So we have one point where the input is x and the output is x squared minus 4x plus 7. And those are like, this is our x value, this is our y value, right? Now we're going to use x plus h. So our input is going to be x plus h. That's like our new x value. But our output is everywhere there's an x, we have to put x plus h instead. So we're going to have x plus h squared minus 4 times x plus h plus 7. So that's our second coordinate, right? Where this is x, this is y, this is x, this is y. And like I said, what we're doing is we're just going to use the slope formula, changing y over changing x. So lots of sort of calculations to keep track of, but this is going to be y2, this is y1, this is x2, this is x1. So y2 is x plus h squared minus 4 x plus h plus 7 minus y1, which is x squared minus 4x plus 7. Conveniently, in the denominator, we're just going to get h, like that part's already done for us. So now all we have to do is we have to just expand and combine and like terms and simplify and stuff. Okay. Here, recall this is going to be a sum squared. So if you know how to multiply sums real quick, this ends up being x squared plus 2xh plus h squared because you FOIL it. Then we're going to distribute that 4 minus 4x minus 4h plus 7. Then we're going to distribute this negative all the way through. So negative x squared plus 4x minus 7. All of that is still over h. Okay, so now we're going to go through our numerator and find all of the like terms and combine them as best we can. Let's use a different color. So are there, yeah, so here's an x squared minus x squared, so those cancel out. Here's a minus 4x and a positive 4x, so those cancel out. Here's a plus 7 and a minus 7, so those cancel out. And it looks like all that's left in the numerator is 2xh plus h squared minus 4h, and it's all still over h. We can simplify by factoring an h out of the top. So we have 2x plus h minus 4 all divided by h. What happens to those h's? Bye. So our numerator ends up being 2x plus h minus 4. So that is the difference quotient for this particular function.